Hi, thank you. I have a hard act to follow. My name is Barriault. I'm actually here to talk about formal methods, especially abstract interpretation, and how it can be leveraged to find hard-to-find bugs, essentially runtime errors. Now, I know that I'm in front of an esteemed crowd. Basically, like earlier in my career, I used to work with that technology, and it was good back in the days. It's even better now, frankly. I think that there's legs to it. It's not the only thing that you should be unleashing to the problem, but I think that this thing has merit and, well, it should be explored. So I didn't know exactly who I would be speaking with, so it's like, okay, where do I set the line? I mean, do I want to be more basic or do I want to go really, really deep? I won't go really, really deep. I'm not a math guy. I'm a practitioner. I work with clients. So I said, okay, let's try to have something that is, first of all, let's talk about formal methods and try to illustrate how they work inside under the hood. Also, run through a few runtime errors in C++ and how you can actually use runtime errors in order to modelize, to modelize the code and find runtime errors in C++ code. Same thing in Rust, because we're being told that Rust is inherently safe, memory safe, I guess is the word. I mean, does it mean that we don't have runtime errors? And finally, just a few ideas about how to best approach mixed code bases, which probably are going to be the norm moving forward for a number of projects. So first of all, let's start with formal methods from a practitioner's perspective. What are formal methods? Let's listen to what NASA has to say about that. Well, it refers to a bunch of mathematically rigorous techniques and tools for the specification, design, and verification of software and hardware systems. Now, in this case, mathematically rigorous, it means that when you're running the analysis, you can actually take it to the bank. It's going to be sound. And it's rigorous logic. That's something that is mechanical. It can be repeated. You can do the math and come up with the conclusions. Then NASA is telling us they provide a means to symbolically examine the entire state space of a digital design, blah, 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 and establish a correctness or safety property that is true for all possible inputs. In other words, no false negatives. You can still have false positives, but if implemented correctly, the promise is that if your tool is telling you that there's no runtime errors, for the runtime errors it can detect, then there is none. You can take that to the bank and it's, guaranteed by math. You can still have false positives, but let us first of all examine a little bit more what it means practically, because sure, I can give you the theory, but what does it mean in practice? Sure, you can take a pen and a pad and start, running the numbers yourself by hand. Most of the time, people will implement a tool. There are multiple tools out there that implement these technologies commercially. Also, there's like academic projects that do the same. You give the tool the information necessary in order to conduct an analysis. It requires some of the code. So basically, it requires compilation closure. Because unfortunately, if it doesn't even compile, it's going to be hard for any tool to do its work. It may require the specifications. It may, not always. So let's just examine that a little bit later on. Now, the tool uses that information to compute the different combinations of values at the specific points in the program. So basically, you have your entry points at different places, like sensor reads or, like just main, basically. And then it takes, but by default, it's full range. And then it cascades all of these ranges through a modelization of what your code does. And based on these computations, it's able to tell you that that x that divides 1, it can or it cannot be 0. So again, proven by math. So if at that point in time, the range is between 5 and 10, you're safe. If it includes 0, Well, the possibility is that you may have a runtime error when you're going to use your macro. And the tool will then use the results of the analysis to provide diagnostics. So again, yes, it will always happen. It may happen. It will never happen, or, well, the code is just not reachable. Now, I told you that what are the inputs that I need to provide to the analysis in order for it to do its work? Well, if you're after functional bugs, so you want to prove formally that your function does what it should be doing, then you need the code, but you also need to inform the tool what are the specifications. So unless you're willing to trust an LLM to do the translation for you, it means that you need to have some kind of formal notations. Let me give you a secret. Well, it's not going to be a secret after it goes on YouTube, but here it goes. I went through a formal methods class in my master's degrees program. It was hard. It gave me a headache each and every day. Oh my God. And this thing, the solver was so slow. And I was like, this is never going to be adopted in the industry. Now, I took a look at ACSL, which, no, I don't want to go commercial on you, but we do implement. It's a lot simpler, thank God. It's a lot more C-like. So it's a lot better than what it used to be more than a decade ago. However, it's still harder. Like, you still need to capture information about your requirements in a formal notation. The trick here is that if you're going after runtime errors, so yeah, your code does whatever it does, but does it do so reliably? That you don't need to have the requirements. You don't need to capture that information. What you need is your code and the assumption, in this case, that at the entry points of your code, it can be anything, it's full range. Now, runtime errors. I'm in front of an esteemed crowd here, and I need to be very careful about runtime errors. Why? Well, let's define them. Usually people talk in C++ about undefined behaviors. Now, some people in sidebar conversations will say, well, in this case, that undefined behavior, I know it exists, I know what it will do with my compiler, so it's not really an error. Granted, I come from the industry, I can tell you that, people that I work with, that's the bane of their existence, because it's very rarely something that they want to see happen. Like, they actually, those are goofs. I mean, they just happen, they are in the code, and they just declare themselves, they just manifest themselves at the worst possible moment, and people lose millions about that. So we're assuming that these are not intentional. So that's my definition of runtime errors. The reason why I say undesirable outcomes, in Rust C, they are not necessarily talking about undefined behaviors, but it's undesirable to have these things in the code. In C++, maybe that it's a division by zero, an out-of-boundary access, overflows, memory leaks. The code may be achieving its goal. So functionally speaking, it's okay, it's just it's not doing so reliably. They are typically triggered by a specific combination of values, which is why it's probably difficult to find them in the first place most of the time. And the consequences, well, it's really random. Crashes, faulty behaviors, security flaws come to mind. And how prevalent is it? Well, if you're in embedded software, MITRE is doing a survey of everything that is happening in the field and gets reported to them. 50% of all the flaws that they have reported in embedded software were overflows. 50%. 70% some kind of runtime errors. In larger systems, that percentage is lower, but it's nowhere near zero either. An image is worth 1,000 words. As I said, I'm not a math guy, so I try to conceptualize things visually. So here we have a blue zone of two integers, x and y. So it's a simplified example, obviously. And the blue here is all the combination of values that can actually happen in a given code. Now, the problem is that in reality, we don't know how this figure looks like. We have no idea. It might actually be mind-bogglingly complex, multiple dimensions and everything. So now, if the combination of values intersect with danger zones here, so basically those are a combination of values where you could actually have errors, then you could have a runtime error. But in the case of the green one over there, which looks a little bit more black here, well, the error is not going to happen because there is no intersection between the realistic value that can actually happen and the values that would trigger that error. So one option is testing. And testing works great for functional bugs. But the problem here is that it's a little bit more complicated. So for example, we're going to have this tester that is going to try to hit different combination of values. Now, again, I'm in front of an esteemed crowd that people that understand how things work. Can we exhaustively test that domain? The answer is no. It's going to take way too long to do that. It's millions of years. We're not going to do that. But the problem is that because we're not going to do that, it brings a question like, when are we done testing? And here's the problem. Like in this case, we have not hit there. If we had a red one here in the middle, we didn't test that either. So, you know, it's a little bit hard to see, but basically the more time you spend in testing, maybe that you can trigger the error by chance, but it's still, you know, it raises a question like, when am I finished testing? And it's something with real practical application. Take Boeing, for example. On one of their planes, the B787, so the larger ones, right? They had a subsystem in there that would actually go off in fail-safe mode after 248 days of continuous operation because of an overflow. Now you would say, yeah, but I mean, for sure, they will reboot that, right? But these planes are flying all over the place all the time. So yeah, it could have happened even in mid-flight. So that was a problem. And in avionics, those are the strictest standards in the world that they are following, like DO1C and DO330. They still could not find it. It came afterwards, after the plane was actually flying. So, all right, so it's not ideal. Can we do better? Well, one way of doing better is through abstract interpretation. Here, what we're going to do is to use the power of math, so theorems that have been around for 4 decades, mostly developed in France, you know, like in French people working at MIT. And we are going to modelize the code again and cascade these range of values throughout our model. So essentially, what we're trying to do is this. It's basically, we're going to have a much simpler form that is going to be a strict superset of all the realistic values. And based on that figure, we are going to be able to come up with some diagnostics. In this case, we know that an error can happen there, and unfortunately, you know, like I didn't interrupt it in time, but there's also a false positive. So that error over there on the left-hand side cannot actually happen, but this is a over approximation, so now we have a false positives. Okay, so what can we do then? Well, we can refine that figure in order to reduce, for example, the size. And we could also have, actually I'm going to put it there. I'm sorry again. So I can also have multiple rectangles, but still it needs to be implemented in such a way to respect the theorem so that approximation is always, 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 always a superset of all the realistic values. But that figure can be actually computed in economical time. So you can have an answer pretty quickly. And if you're a bit lucky and you do that right, then eventually you still detect the error because, yeah, sure, it can happen, but the other one cannot. So the precision of the analysis increases. Now let's talk a little bit about false negatives and false positives. Now, false negatives, it's basically there's an error, the tool tells you nothing. Bummer, because you much would rather know about it, right? But in our case, in the case of formal methods, abstract interpretation, it's guaranteed never to happen. So the math works, it's never going to happen. If the tool doesn't tell you anything, it means that there's nothing. Now, false positives may still happen. There are two ways you can consider that. First of all, you have the case of I didn't implement my algorithm to the fullest extent of its possibilities. Maybe that my implementation is a little bit sloppy. Or maybe that I'm not spending enough time refining the numbers. You know, like there's a trade-off there for sure. But here's the other thing. If we make abstraction of this and we just focus on, okay, I have this code, it's a library, for example, and I'm assuming full range of all of my input values. C++ is not a strongly typed language like the way Ada is, right? So you could say we're really taking the worst case scenario, which actually it's exactly what you might want to be doing. Say you have a library, you have no idea who is going to use your library and how. So it could be anything. Or maybe it's something that needs to be extra solid because if for whatever reason you have a runtime error in there, it's bad news for the whole system. But again, I'm a practitioner. Many of people here are practitioners. You may actually say, you know what, full range is not necessary in this case. Here's why. My code is never going to be used outside a certain context. So sure, that unsigned char, in theory, full range from 0 to 255, but in fact, I'm never going to have any value over 200. You can actually feed that to the analysis. Then you're going to have a different answer. It's going to lower the number of alarms, potentially. Of course, if your hypotheses are not holding, then it means that maybe some errors are going to be ignored. So, the no false negative is true so much as long as your input values are of the proper range. By default, if it's full range, you're good. If you choose to make it something else, that's up to you. With great powers comes great responsibilities. So this is like the theory. Let's take a look at it in practice. So with a few very simple C and C++ code. So as I said, out-of-bound array accesses actually tend to happen a lot in the field. They do. So for example, in this case, it's a bit difficult to see, but I think that everybody is going to find it right away. Length superior or equal to 0 in a while loop. That's usually your cue to say like, I think that there's something wrong there, and you would be right. In this case, we're basically trying to write one more item on the right of our array. So in order to implement formal methods in this case, you need to keep track of arrays and how they would be apportioned onto memory. Now, of course, the way that it will be done ultimately is implementation dependent, but you need to keep track of the boundaries. So if it goes over the boundaries and you're trying to either read or write from there, you should actually flag it. Now, if that's what you want to do, then you feel free to disregard, but most of the time, that's not what people want to do in the first place. And as I said, the overflows are unfortunately happening a lot in the field. in this case, that very same piece of code, once you make abstraction of that while loop that can go out of the bounds of the array, there's an overflow. And that overflow can actually happen in this case for all the values that I applied to. So in this case, I ran 1,000 times. But it's also a property of formal methods to keep track of the range of values, even like during for loops. At some point in time, maybe you want to fold them together and say like, well, moving forward, I'm not going to have that many ranges. It's going to be a merge range, for example, for just keeping things moving. But all else being equal, we can keep track of the range of values even in different loops, and then come up with conclusions. In this case, yeah, it's full range, and then I increment 1. It's signed, so it's undefined. We don't know what's happening next. Now I said, look, this is C++ conference, right? So C is fine, but let's have something more C++-like. And I came up with that example, has been provided by our R&D group. Apparently, that's something that they saw in the field. Can somebody tell me where's the bug? Maybe that's going to help. This is what I call disambiguated steps. It's actually trying to reflect, here's the C++ code, like the way that it looks like. Here's all the steps that it goes through. And you notice that actually once it's disambiguated, then you have those waving brackets that are being added. And what it really tells us is that, okay, I'm trying to build bar. As part of building bar, I need to build foo, but then foo goes out of scope. It goes out of scope. It's easy to miss. So when you're going to try to access X, which is part of foo, it went out of scope. And unfortunately, in this case, well, it's going to result into less than ideal execution. So again, for formal methods to do its work, it's one of the things that needs to be done. It's like you need to understand, based on the standard, how is that code here going to be translated to different steps. So that's how it's able to keep track of that. And you do also need to keep track of how the structure of the class will be represented in memory. Now, the consequence here is that we have pointers that are pointing in random places. It's probably not a good idea to have them there. Now, let me also make another confidence that is not really one, because this is going to be on YouTube. But when people approach me and said, like, look, let's do a presentation in C++ now. Oh, by the way, they want us to talk a little bit about Rust. And I was like, C++ conference, really? I mean, isn't that like, no. I mean, it's interesting. And, during the previous talks, I mean, I saw a lot of people being open-minded, right? And saying, well, there's some teachings maybe are coming from the Rust community. Now, I'm not a Rust guy. I had to brush up on that. I'm much more of a C++ guy. But I said, okay, like Rust is claiming to be at least memory safer. Why is that? And how is that happening? So maybe that, again, based on what Lisa said, maybe that there's some things that you should not trust me on, because I'm not the top-notch expert. But based on my analysis, is that the premises of Rust is to prevent users from building code that is risky by policing what people can do. So there's a few more locks that you have to deal with than in C++. For example, all variables are constant, unless you make them mutable. Now that one, I was smiling. It's like, well, it says variable, right? So I mean, it should be variable. But they chose to make it this way to make it absolutely explicit. But the big enchilada is basically maybe the smart pointer that owns objects on the heap that Lisa explained much better than I could, like this morning. Where you can have very complex borrowing rules where you say, well, if you want to write, it's only one Barriault, but you can have as many as you want for reads. Oh, you want to read and write? Well, no, it comes one again, etc. So maybe I'm going to be a bit controversial here, hopefully not, but that makes me think of that. It's not bad. I mean, it's like my daughters needed this because otherwise it would have been very difficult for them to learn how to properly operate a bike. So have safety wheels? That's great. But does it mean that we solved the runtime error problem? Unfortunately, not quite. Just like my daughters found out soon enough that, yeah, it's possible to fall from a bike with safety wheels on. It's more difficult, but it's possible.
Depends what you do.
It depends what you do. It depends if dad is pushing too.
Well, it's an analogy, right? But if you turn too sharply with those, you'll fall in cases you don't fall otherwise.
Exactly. And it's pretty much the same here, because in Rust, you can have runtime errors, first of all, in code that is unsafe, but also in code that is safe. So not declare unsafe. Let's go through that. So first of all, unsafe, Rust, code unsafe. Yeah, there is a mode of operation in Rust where you say like that block of code is declared unsafe. And the reason why the Rust folks provided that is that they said, look, static analysis is conservative. So by default, if we're not sure that this is safe, we're going to prevent you from doing that. But we realize that in some cases, that may be a bit of an overkill. It may actually hamper people from doing exactly what needs to be done. So we are going to provide them the power to override, to a certain extent, our security procedures. So for example, if you're doing low-level hardware accesses, you know that the hardware may actually change the values between two reads. Well, that's unsafe. That's the equivalent of volatile. Performance enhancements that are not otherwise available. It's another typical utilization. Calls to functions written in other languages like C++, and also convenience. So trust me, I know what I'm doing. Well, don't trust me, but trust me, I know what I'm doing. The unsafe superpowers are based on the Rust book are as follows. One of them is to dereference a raw pointer. So you point in memory and you say like, please read there. It's not, the Rust book says it's not to be frowned upon. It's not something that is shameful for you to do. It's just that when you declare something unsafe, you understand that you're taking a little bit more risk. So for example, if you have this code in Rust, which is basically, it's trivial, right? I'm trying to print something at an address, a random address. It's coming from the Rust book. If I try to compile this, it's not going to let me do it. But if I make it unsafe, like this, then it doesn't have any problem letting me do it. The consequence, of course, is that if I'm in user space, probably a segmentation fault, and if I'm in the kernel space, we're having fun. Formal methods here, well, again, in order to implement formal method, you need to modelize memory access, inclusive of absolute addresses such as this. It's true in C++ and it's true in Rust. You need to let the tool know that, yeah, these raw accesses are actually valid on your hardware. Otherwise, it says, well, like, where are you writing in? But there's a way usually that you will be able to do that because you need to. Again, here we're going to assume that it can be anything, so the equivalent of volatile in C++. And you also have the need to implement the ability to detect potential problems during pointer arithmetics. But the most interesting thing, obviously, is runtime errors in safe code in Rust. So, if a dangerous operation is not forbidden by the compiler, so Rust C didn't come after you with a blowtorch and said, you're not going to do this. is not a recoverable error. So they have this concept, like for example, for conversion operations, like often it's being embedded into another entity with a potential error that is being passed on. Now, if you don't want to bother, you can actually call what they call unwrap, and then you just access the results. So if you're just calling unwrap, so you're completely disregarding that security feature, so basically you're voiding warranty, or if it is not a recoverable error, so there are errors that you just cannot recover, and you experience the right combination of values at runtime, what happens next is that the thread is going to panic. There is no way, based on my research, and I try to research a lot, there's no way back to normal execution. It will go out, which may not be a problem if you're on your computer, it just reboots. If you're in a plane and it reboots, that's something else. So unfortunately, you want to be a little bit safer. Take this code. This is coming from the Rust code, so it's trivial, right? I could have made it a little bit more interesting by replacing 99 by something else, but essentially here, it will compile, even if the code is not marked unsafe. I tested it, it works, it will compile. It will call for the panic macro during execution because obviously I'm reading from somewhere I shouldn't. As such, it's going to give me a nice message. So if you're on a computer, that's nice because you're getting access to all of your standard errors. Unfortunately, often I'm dealing with systems where they're embedded. The standard errors may not be readily accessible, so I might not get that message immediately. Formal methods, again, here would be able to find the error here, even if the out-of-bound index is a result of a complex calculation. So even if it's not V99, if it's V of X, and X depends on a number of sequences of operations throughout a very complex stack, it's going to be able to determine, okay, like X at this point in time can be superior to 2 or not, or inferior to 0.
Won't there be, if the calculation is complex, won't there be false positives?
There could be. There could be. I mean, there's different strategies that you can adopt in order to reduce the number of false positives, but unfortunately, in order to have no false negatives, there's always a possibility to have a false positive, for sure. Now, out-of-bound array access is not a recoverable error, and you could handle it, like you could do something like this, where you're matching and you're kind of verifying if you're returning something from that access, and say like, well, if I'm returning something, then I'm fine, and otherwise I'm not. But this is not different from defensive code in my view. You could do the same thing in C++. Division by zeros in Rust code, yes, that's also possible. So in this case, we have we're verifying something, we're calling another function called decrypt element. And what formal methods are telling us is that what can come out of there in the ACC ranges from 0 to 10,922. Now in this case, unfortunately, it includes 0. If it just ranged from 1 to 10,000, we would be safe. But 0 is there. So there is a chance that when we finally return at line 34, that there's going to be a division by 0. Here's a quote from our CTO that I found. I translated it from French, but I found it funny. He said, like, basically in Rust, it will stop violently, but cleanly. It's going to give you a nice error message if you can read standard error, which in my case, maybe not. In C++, it's a little bit, it may stop violently, it may not be so cleanly. Maybe that, for example, if you're doing something and you corrupt memory, not in this case, but in cases you corrupt memory, nothing happens, and then eventually it reads from that memory allocation and oop, now you don't have the right value. So it's still not good code in general. It's just that Rust would tend to be a little bit more forthcoming with, I'm sorry, I'm going to panic and exit. It's still not good. So is Rust safe? It's safer. It's safety wheels. I think that the analogy is apt. It helps, but there's more cost on the developers. I mean, it's more constraining. That's number one. Number two, you can still have runtime errors, both in unsafe code, obviously, but also in code that is not declared unsafe. And some of constructions in C++ can be also used to mitigate some risks, such as smart pointers for heap objects. So that it's not necessarily that Rust is certainly innovating, but there are a lot of things that can be done in C++ that can actually mitigate this risk exactly the same way. And formal methods, the application of formal methods in both cases is exactly the same. It's like basically keep track of memory, keep track of what you're declaring, have that modelization of the code, and keep track of the range of values that are possible at the entry point. By default, full range. Cascade that and see if something fishy can actually happen. So here's a question. We know that in the future we're going to have more interrupt between C++ and Rust. Should we analyze them together? Is there any value in there? Well, if you think about it, right now we have a lot more people that are investing in Rust, but they also have significant C++ code bases. So you should expect that at the very minimum, you're going to have interrupts. And this is basically me speaking. You know, it's not necessarily my company, but the way I see it is that C++ has been around for ages. It's still going to be around for ages, both for new products, new code development, but also for the interrupts. I don't see this being any other way. So under these conditions, again, how do you verify mixed code bases? As two separate objects or as one unified project? If you're thinking about it, there are advantages and disadvantages to both. Say, for example, that you're analyzing C++ on this side and Rust on the other side, and you're assuming that anything that can come inside these two systems can be anything full range. Advantage, robustness is probably going to go up. Disadvantage, you're going to have more alarms to deal with potentially because now the range of values is larger. But that may be actually what you want to do because you're saying, today I'm using it in that context, tomorrow I don't know. Or maybe that there's going to be a developer that is going to be joining my team in 6 months, and that guy will not know that you should not pass certain very extreme values. On the other hand, you could have a more pragmatic approach and say, in this case, I really, really want to minimize the number of so-called false positives. It's not really false positives here as much as it is, those are values that cannot really happen because it's being used in that context. If that is the case, then you can actually use it as one project. So it works, like we've proven it to work, where you could have C, C++, and Rust code actually being put in one analysis and run the formal methods over that. It can be done, and it reduces the number of alarms because of that. So finally, simple overflow example. Again, nothing to write to your mother about here, but in this case, there may be an overflow. If I analyze it in isolation, it's trivial, but there could be one. But if I write a C++ code that is calling that Rust code with a single value, then in this case, there will not be a bug. Or I could actually call here with a range of value. But as long as I'm not including the max, then I'm safe. Yes?
So are you doing context-sensitive analysis?
I'm sorry?
Are you doing context-sensitive analysis?
Yes.
Procedural analysis?
In this case, it's context-sensitive analysis, basically. Yeah. So conclusions, Rust, just like any low-level languages, can still have runtime errors. Formal methods can be used to find runtime errors exhaustively, so no false negatives proven by advanced math operations. And again, with the provision that by default it's full range, you can make it something else. And this is exactly what I'm saying here. You can actually reduce the number of perceived false positives, which are not really false positive in this case. It's more like, well, I know that this is not going to happen because I'm not going to be using this code in such a way. So you can actually tweak the analysis in order to have improve resolution or improve precision of that analysis. Now, finally, I would be derelict in my duties if I didn't recognize that I got help putting this presentation together from my CTO, Benjamin Monat, and also Stefan Zimmerman. Taught me a lot about Rust, so that's excellent. Thank you both. I would like to thank you, the organizers, for inviting me. I mean, it was fun. I knew that it would, from the other presentations, like it's a nice intellectual crowd. That's what I would say. It's like it led to a lot of very good discussions, which I'm hoping to have again. And all of you, and of course, thanking all of you for attending. And this is my name, just in case that you have more questions. Could be anything you want. I will also leave you with my LinkedIn profile. Mike Sherman is my colleague. He's also here. And I believe that you have shirts for everybody.
Anybody would like to join the orange team.
Yeah. So,
I do not want to take them back to Denver with me. So please take
yeah, we have a fire sale. It's free. But any questions?
So this is a software tool that you're developing.
It's a software tool. I mean, obviously here I invested the time to explain the technology, right? Mm-hmm. So nothing that I said is specific to our tool. We can have that conversation, obviously.
No, I'm just interested. This is what you do.
Yeah, that's what we do. Yeah. So what we do at Trust and Stuff is an implementation of formal methods / abstract interpretation to detect runtime errors.
Are you in France?
Actually, I'm located in Boston. He's located in Denver. Our company is French. Most of the people that are doing abstract interpretation tend to be French. There's a center of specialization somewhere in Paris and in Grenoble. Mm-hmm. But yeah.
Okay. You work with Thales, I guess.
That's one of the
yeah.
You're analyzing the source code, right?
Yes.
Not what the compiler produces.
Exactly. So what we cannot do is to detect the consequences, because that's, implementation dependent, basically. So for example, we don't do also the optimization. So we can tell you, for example, there's an error there. We don't know if the compiler through the optimization is going to make it go away. Maybe you're lucky, right? But
no, I'm thinking more of, you have a certain class of errors you're detecting.
Correct.
But if my code is triggering an undefined behavior you're not looking for, then you will not only not catch the undefined behavior, you won't catch the optimizations or the consequences that leads to.
So most of the tools that have been implemented out there, they go after, like I would say, runtime errors that are very frequent. So out-of-bound arrays, division by zeros, overflows, and so on. There may be runtime errors, frankly, that where say, okay, we don't have coverage on that. My CTO shared a number of features from C++ 17, if I remember correctly. And it's like we pretty much cover all of them, except maybe one. But, after the call, if you're interested, let me know and then I can give you more the details.
No, I got the...
Yeah,
okay.
The gist. Yep.
One thing I'm kind of wondering about, it was a very interesting presentation. Thank you.
Thank you.
So it seems like if you're kind of incrementally developing from scratch with a tool like this, it seems like it can, if the code base grows up with it, it gives you a really good level of confidence in terms of the code that you're shipping. the main thing that I wonder about is that, like, if you take like a large pre-existing C++ code base and kind of try to feed it into this, like, I just wonder, do you guys have experience with, like, practically speaking, how that goes, or kind of challenges or like strategies that you could use to try to mitigate that? I'm just afraid, like, where I work, I would just get such an output of problems.
No, we do.
Yeah.
I understand, and it's your point is well taken. It's like ideally, those kind of tools, like not only that, but also other tools you give to the developers, and you say like, look, it's like if you're doing a carpentry, right? You will have a ruler, you will have a level, because you just don't want to just guess.
Mhm.
You want to have some kind of feedback that can help you improve the code, and that's the best utilization. But truth be told, you have code bases out there that are already existing, and you don't know where to begin, right?
Mm-hmm.
So one of the ways that you can do that is to ask yourself, like, in that code base, what must not fail under any circumstances? Like, we have an example of a large client we have where they said, well, here's a firmware. If security is defeated there, try as I may to make things safer elsewhere, I'm doomed. So, like, focus there. So first of all, there's a prioritization. Second, like, when you're using the analysis, there's nothing that says you need to analyze the whole code all at once. Personally, I did some research with OpenSSH, okay? And at the beginning, I just said, okay, like SCP, I'm going to just analyze everything at once. Actually, I ended up revising that approach and said, oh, here it tends to branch out a lot, right? So I'm going to divide it into modules that actually kind of work together in order to restrict the time spent analyzing. And then the number of alarms that I had to deal with is a lot smaller.
Right.
So that's another way to
But
do
you
that.
get more false positives this way.
Not necessarily. I mean, it depends. It's
Because the module boundary, you kind of assume full range, whereas if you analyze
Yeah.
everything...
no, you're right. Yeah, no, absolutely. You might get more false positives. At the same time, you get more reusability. So there's...
No, I'm not saying it's a bad idea. I'm just
Yeah.
saying there is a trade-off.
There's a trade-off. If you want to avoid that trade-off, you could say, well, I'm going to stipulate that my entry values are not full range. You could do that, but is that a good idea or not? The tool lets you do it. The technology lets you do it. Whether or not it's a good idea might not be. Like in your case, yeah, go ahead.
Can you do the opposite? So say you analyze the model and you say, I'm assuming the inputs here are not full range, they're this.
Yep.
And then when you analyze the flip side, you define it as an error to violate this range. Can you do that?
You could. Actually, an assert, right?
Right.
Could do an assert if you wanted. But yeah, that's intriguing. Yeah, it's like if I define my range and then after that, one thing that you could certainly do is that you analyze it within the functional ranges that you define, and then after that you do a comparison with a full range and you say like which alarms are actually popping up. That could be another way to do this. But I'm not answering your question like you're looking at me like so.
No, that has to do with the time and the jet lag.
Okay. No, I just want to make sure that I answer all the questions. So we're at time, but if you want, if you don't want to be on YouTube, but you still want to ask questions, like feel free to ping me. I don't bite. But otherwise than that, thank you very much for being a very nice crowd and for attending. I appreciate it.